and we continue reviewing our four. We're going to look at the extra problems beyond what College Board reviewed. So problem 7. Suppose two events E and F have non-zero probabilities P and Q respectively. Which of the following is impossible? So what we're going to do is we're going to try and make up counterexamples to show that it's possible. So for the first one, by the way, E and F don't have to be related at all. So I could actually give E a probability of 0.6 and F a probability of 0.7. And so it could be it rains and there's a car accident. So those can be totally unrelated, right? Or semi-related, but they don't have to be the same thing. So if P is 0.6 and Q is 0.7, look at that. I add them together and I get a number greater than 1. And guess what? I can also use them for the next one. I subtract and I get an answer that's negative. And remember, this B choice here is actually kind of common. All you have to do is switch the order, and one of them is going to be smaller and one's going to be bigger usually. So you can totally get a negative. And also you can switch the order on which one's bigger. So let's say I make P bigger and Q smaller. And I say, 0.4 divided by 0.2, I get 2. So C is totally possible. Now let's look at the next two. E and F are neither independent nor mutually exclusive. So what does independent mean? It means if I multiply my two probabilities, then they should equal the probability of the and, all right? So if I take, well, let's say I use the numbers from here and I say, 0.4 times 0.2 is 0.08, but it's actually not that. So what that could mean is that it is independent, all right? So, I'm sorry, not independent. So this part is fine. And all I have to do to say not mutually exclusive is that the probability of E and F is not 0, all right? So it's exclusive if it equals 0. It's independent if the product, this right here, does give you the probability of E and F, all right? But here I show you, okay, here's the probability. I'm just making one up. There's no reason it can't be that. And there's no reason it couldn't be that probability here, which shows you that the probability of E and F are neither independent nor mutually exclusive. So D is fine. Now, if it's independent, the probability of E and F must equal the product of P and Q. But it also has to be 0 because it's exclusive. Well, that can't happen. Statement E is impossible. So if you're exclusive, then the probability of both of them happening is 0. But if they're independent, you got to multiply the probabilities together. And they did say they're non-zero probabilities. So that's why it's choice E. Number 8. An inspection procedure at a manufacturing plant involves picking 4 items at random and accepting the whole lot if at least 3 of the 4 items are in perfect condition. If in reality 90% of the whole lot are perfect, what is the probability that the lot will be accepted? So first of all, you probably see I already had this up here. This is a binomial distribution with 4 attempts. The probability the item is fine is 0.9 or perfect. And we're looking for the probability that at least 3 of the 4 items is great. So what I'm going to do is I'm going to substitute in here. Now I got to work out 2 sets. One where x is 3, and then it can go all the way up to n, in which case that's the next number, 4. And so what I'm going to do is work out a substitute in this formula with n is 4 and x is 3. And then I'm going to do this again where n is 4 and x is 4. So it would be combinations of 4 choose 3, 0.9 to the third, times 1 minus 0.9 to the 1, or in other words 0.1. And 4 choose 4, 0.9 to the fourth, times 1 minus 0.9 to the 0. So 4 choose 3, you can do the math on your calculator. But basically, if you have 4 things to choose from, and you're going to take 3, how many different ways can you pick the 3? There are actually 4 ways to do it, because in reality, you're just picking the one you're leaving out. Now, if you have 4 things to choose from, and you're taking all 4, there's only one way to do that. So that's why you don't have a number in front of here. And that's why you have a 4 there. And then this part kind of matches on the front. You have 0.9 to the third and 0.1 to the 1. Then you have 0.9 to the fourth. Remember, that's 1 again. So this is 0.9 to the fourth, and anything to the 0 power is 1. So that is why the answer is E. Number 9, a town has one high school which buses students from urban, suburban, and rural communities. Which of the following samples is recommended in studying attitudes for tracking of students in honors, regular, and below grade classes? So the population is divided into representative groups, which are strata. So the groups have something in common, and random samples are selected from each group. So in this case, we might want to look at urban, suburban, and rural communities separately because there could be differences in them based on which strata they're in. So a stratified sample would be recommended. Number 10, suppose there is a correlation of R equals 0.9 between numbers of hours per day students study and GPAs. Which of the following is a reasonable conclusion? So if you look at your F2 notes, it tells you about this thing called R squared. So R squared is the coefficient of determination, and it represents a percent of the variability in the response variable that is explained by the explanatory variable. So if I square my n, my R, so 0.9 squared, 0.81, that's how we get this 81% of variation in GPAs can be explained by the variation in number of study hours per day. So again, coefficient of determination, square your R, and it shows you the percent explained. If you want to know the unexplained percent, you just subtract that number from 100%. So we can say that 19% of the variation in GPAs is not explained in the number of study hours per day. Number 11, to determine the average number of children living in single-family homes, a researcher picks a simple random sample of 50 such homes. However, even after one follow-up visit, the interviewer is unable to make contact with anyone in 8 of these homes. Concerned about non-response bias, the researcher picks another simple random sample and instructs the interviewer to keep trying until contact is made with someone in 8 more homes so that he has his sample of 50 homes. The average number of children is determined to be 1.73. Is this estimate probably too low or too high? So we're going to say homes with children are probably more likely to answer the door. They're probably home more, they're not out as much, and the homes that don't answer are probably more likely not to have children. So the homes that didn't respond. Well, they're going to replace those homes that didn't respond with homes that do respond, which means they're probably going to have a little bit too many homes with kids. So it's going to be too high because of undercoverage bias. Number 12. The graph shows cumulative proportions plotted against land value in dollars per acre for farms on sale in a rural community. What is the median land value? So the median is at the 50th percentile, or 0.5 on a cumulative distribution function, which would be right there. So as I go across that, and then I drop straight down, I get 2,000. So $2,000 per acre is the median value. Number 13, a confidence interval estimate is determined from the monthly grocery expenditures in a random sample of n families. Which of the following will result in a smaller margin of error right there? So let's remember margin of error is critical value times standard error. So if we use a smaller confidence level, that means we'll have a smaller critical value, so our margin of error will be smaller. So choice 1 does work. Choice 2, a smaller sample standard deviation. Yes, a smaller SE will definitely make the interval smaller. It makes it smaller. Then smaller sample size actually increases the standard error, making the interval larger. So just 1 and 2 will work here. Number 14, a medical research team claims that the high vitamin C intake increases endurance. In particular, 1,000 milligrams of vitamin C per day for a month should add an average of 4.3 minutes to the length of maximum physical effort that can be tolerated. Army training officers believe the claim is exaggerated and plan a test on a simple random sample of 400 soldiers in which they will reject the medical team's claim if the sample mean is less than 4 minutes. Suppose the standard deviation of added minutes is 3.2. So we're actually talking about sigma. So they're going to reject if our sample mean is less than 4. there's our true standard deviation, and there's our true mean. So I went ahead and wrote all these down, and we remember that we're actually taking samples of 400. So my sampling distribution will have a mean that's the same as this population mean, which is 4.2. And then I just have to adjust my sigma for the sampling distribution. So I divide by the square root of the sample size. So I'm going to divide by 400, square root of 400. So then I can go ahead and substitute in my statistic. So they're saying they're going to reject if it's less than 4. So the 4 goes here, the 4.2 goes here, and then we're going to use this formula for the standard error, which gives us that. So it would be this one right here. Now, one way to think about it, again, this would be a normal distribution because we know the standard deviation, the true population standard deviation. We adjust it for sample size, and this is the model that we would have. The true mean is 4.2. There's my true standard deviation, which is just basically 3.2 divided by the square root of 400. And here is the actual probability that you would reject the null.